Good morning.
Good morning.
All right, so last class we finished the lecture slides from chapter 10. So we're on to the example problems from chapter 10. So we'll get started on those. Let's do -20. Okay. All right, so it says repeat problem 10-19, assuming isentropic efficiency of 85% for both the turbine and the pump. Okay, so 10-19 says consider a 210 megawatt steam power plant that operates on a simple ideal Rankine cycle. Steam enters the turbine at 10 megapascals and 500 degrees Celsius and is cooled in the condenser at a pressure of 10 kPa. Show the cycle on a TS diagram with respect to saturation lines and determine A, the quality of the steam at the turbine exit, B, the thermal efficiency of the cycle, and C, the mass flow rate of the steam. Okay, so we're given then this ideal Rankine cycle. Okay, we have the power. It says a 210 megawatt steam power plant, so that'll be the net power output. Okay, we also from our problem has isentropic efficiency, so I'm going to put those down. We have the turbine is 0.85 or 85%. The compressor is 0.85 or 85%. And then we have steam enters the turbine at 10 megapascals and 500 degrees Celsius. Okay, so that's going to end up being state 3, but if you're not sure, like when you're doing the problem yourself, you can just leave that subscript blank and then come back to it. Okay, but it's 10 megapascals, 500 degrees Celsius, and then it's cooled in the condenser to pressure of 10 kPa. That'll end up being pressure 4. And again, if you're unsure, you could just put P condense and then come back and put your state numbers on it. We need to do TS diagram, which we would do anyway. And then they tell us to find we have A, the quality of the steam at the turbine exit. That'll be state 4. Say turbine exit quality, which is state 4, quality X4. And then B is our thermal efficiency. And then C is our mass flow rate of steam. Okay. Put up our schematic. Got our pump. That goes into our boiler. And then we have on the outlet of the boiler is the turbine. And then out of that, we have our condenser. And then we go all the way back into the pump from there. All right, so let's label. We got 1 is our inlet to the pump, 2, outlet of the pump, inlet to the boiler, 3, outlet of the boiler, inlet to the turbine, and 4 is the outlet of the turbine, inlet to the condenser. Okay, so this is our condenser. All right, so we have some work of the pump here. We have work of the turbine here. We have some heat in the boiler and heat out from the condenser. All right, so then we have our schematic laid out, and they told us first off to do our TS diagram, right? It wasn't even in the signs. That's how important it was. The question. So the ideal Rankine cycle is the same. So it's pump, boiler, turbine, condenser. So just like in the Brayton cycle, we had compressor, heat exchanger, we're adding heat turbine, other heat exchanger to reject, right? So it's kind of the same setup, except we're raising the pressure of water instead of gas, so we have a pump. All right, and then we're changing phase, so we call it a boiler, right? Because we're heating it while we're changing phase, so that's why we call it a boiler, but it's just a specific type of heat exchanger. And we still have a turbine, right? And then we're condensing, so we're again heat exchanging, but we're rejecting heat, so we're changing phase to the condenser. Okay, so the layout or the schematic from the Rankine cycle to the Brayton cycle is very similar. Okay, but yeah, that would be something. I think most problems I would give them to you, the schematics, maybe not the simplest ones like that. It's just if it's just the simple Brayton, simple Rankine, simple Otto, simple diesel, I don't necessarily think I might not give you the schematic and just expect that you would know it or be able to get it very quickly. If it has anything special to it, then I would put that on the problem. I would show the schematic. All right, so first off, it tells us that TS diagram, right? Here we have a vapor dome. And let's see if I can draw it on a screen. All right, that's better. So we have in the Rankine cycle, we end up having, in this setup, we have 2 pressures that we're operating between. All right, we can look at the schematic. The pump changes pressure and the turbine changes pressure. The boiler and the condenser do not change pressure, right? It's a heat exchanger. The pressure doesn't change through it. So we have just two pressures, okay? All right, so then we're going to start at our state one, our inlet to the pump. In this case, is the inlet to the pump is state one, because that's where we're at our lowest pressure and temperature and quality, right? So state one, we're right here, okay? Quality is 0. It didn't even tell us that, right? But it's the inlet to a pump. Then if we're isentropically compressing in the pump, right? Raising, let's see if I can maybe zoom in to do this one. All right. So that would get us to 2S, right? If we're isentropic. Well, we have isentropic efficiency. So just like last class, we did that for the turbine, we have one now for the pump. So that would take us a little bit to the right on the same pressure line. And that would take us to 2 actual right there, because same inlet and outlet pressure, but we have a little bit of irreversibility, so our entropy increases. All right, so now let's try that again. I'm trying to do a dash line here that's visible. All right, so then we get to 2 actual, right? Now when we go through the boiler, we're adding energy, we're adding heat, we're adding energy, so then that makes us add entropy, right? Along the same constant pressure, because we're going through a boiler. And we end up, actually, let's not go so far. Let's say we'll end up here, okay? So state 3, right? Now we're going through the turbine, and we're expanding. If we expand isentropically, we end up down here, 4S, but we have an isentropic efficiency, so we have irreversibilities go into the outlet. So we end up a little bit to the right with 4 actual, okay? And now we go through our condenser, and that takes us back to state 1, okay? We can add our labels. This is where we have heat in, heat out, because we're going from right to left. We're reducing entropy because we're rejecting heat, right? We have work going in at the pump, work going out at the turbine, all right? Any questions on that? All right, so then we have our schematic, we have our TS diagram. Really now it's just then analyzing the problem, okay? Sorry about that. We need the turbine exit quality is the first thing they're asking, okay? in part A. What I will say in these problems, especially, and you could have done this in chapter 9, it's not as important, but in these 10 and probably some of the 11s, what I'll do, and on these problems, this is what I do, is we'll create a state table. Okay, so like state, then we'll have temperature, then we'll have, so let's make this a little smaller. All right, so let's do, we'll have state, and we have our temperature again. Then we have pressure in kPa. We have enthalpy in kilojoules per kilogram. Entropy in kilojoules per kilogram K. We have quality, and then we might need some specific volumes. Okay. And in this problem, we have a state 1, we have a 2S, we have a 2 actual, we have a 3, we have a 4S, and we have a 4 actual. All right, so we're making this table basically to better organize all this state information, right? It's not so bad when we had just 1 or 2 states where we could just say state 1 and then bracket it and just show what that value is, or state 1, 2. But now when we have these different states, we have 4, but there's these isentropic ones. But then at each one, we have all these different properties we might need in this problem. So trying to keep it organized and just writing it someplace on your sheet of paper and then trying to find it when you go back and looking at that sheet of paper when you need it later in the problem as you're solving, it becomes difficult to keep organized and find that information. So the table will help it a great deal, okay? So also we can start filling in what they gave us. Okay, so they gave us, initially, they gave us the inlet to the turbine, right? So that was 500. So they gave us this one. Okay, I'm starring it so we remember what we got as our initial when they gave us in our givens. We added 10 megapascals as the inlet to the turbine, which is 10,000 kPa. All right, and then we got the condenser pressure, which is 10 kPa. So that would be 4 here. All right. Is there anything else we can get here for the table and fill in, knowing our schematic and our TS diagram?
With state 1, maybe?
What was that?
Maybe we can also add the quality of state 1, x equals 0.
Yes, so we have the quality is 0, right? I mean, it was given, but it wasn't given, right? Since we know it's an ideal Rankine cycle, we know the inlet to the pumps is 0, okay? So that's something we got to recognize. So we know that, okay? Anything else?
Pressure 2 and 3 should be the same.
Yeah, so we know the pressure at 2 is the same as 3 because we're going through that boiler, okay? And flowing the fluid through. Okay, so we have that. State 1, do we know anything else about state 1? Yeah, state 3 is superheated, yeah. So there'll be no quality on that. But state 1's pressure, right, from our diagram, it's the same pressure as 4. Okay, so that's the other thing we know. So that means, if you remember from properties, right, and this is water, all we need is 2 independent intensive properties, right? So that means for state 1, we have pressure and quality, so we can get every information we might need, okay? So we're kind of set there, okay? State 5, because as mentioned, it was superheated when we checked this out. So that means that's also fixed, since pressure and temperature are independent in the superheated range, where we have 2 independent intensive properties, and our state is fixed at state 3 also. Okay, so we can get anything we want. I don't like to fill in everything just because it's a lot of information. I'll fill in just what we need as we need it, right? So I don't want to just grab a bunch of properties because it could end up being time consuming getting more properties than we need. Okay. All right, so we're there. Okay, we have our table at least initially filled out. I will get enthalpies for these, and then we can see whether we need anything else. So for those 2, we have an enthalpy, okay? All right, so let's go back to part A. It says the turbine exit quality. So that's going to be this, right? So we're ultimately looking for this guy, right? Quality at the turbine exit. Can we get any information for state 4 or 4S, for actual 4S?
The entropy at 3 is the same as the entropy at 4S.
4S, yeah. So we can grab our entropy from the tables, and then 4S, as we go, right, we see our diagram, the entropy is the same, okay? So that means we have 6.5995 here also, and now the state at 4S is fixed. We have 2 independent intensive properties, so then we can get everything we want there, okay? So I'm going to grab the enthalpy, okay, there. And then we can also, to get that, value, we had to get our quality, right? So that's why I have the quality for that state. All right, so now we still need to get the quality and information at 4 actual. How can we get from state 4S to 4 actual information?
Using the isentropic efficiency?
Yep. So we utilize the isentropic efficiency. Okay, so for the turbine, we have an isentropic efficiency, right, which is our work actual over work isentropic. Okay, so plugging in, just change in enthalpy. All right, if we wanted capital W, it's mass flow rate through each, and then the mass flow rate cancels and we get to the lowercase work. Okay, so we see this, we go through, we have our turbine efficiency. We have enthalpy at state 3 because our state was fixed and we grabbed it. And then we said we ended up getting our H4S because this was isentropic. Right. All right, so then that means the only unknown is H4 actual. Okay, so we can utilize this equation to get H4 actual. So we get 2282.5, and now we have two independent intensive states between at state 4 actuals. So these are our two independent intensive properties. Sorry, not states, two independent intensive properties. Our state is fixed. That means we can use that to get our quality. So we get 0.874. Okay. Any questions on that?
If we end up with like a number that doesn't really match the chart, can we like loosely base it on what we have, or would we have to
It doesn't matter. So that's because it was interpolated for a lot of them, right?
Yeah, okay.
So it was linearly interpolated to get the values. All right, so then we have the turbine, and then that's part A, so that's done. Part B, thermal efficiency. All right. And the thermal efficiency is the same because it's a heat engine, right? So we have work net out over Q in, right, which is the work of the turbine minus pump over Q in, or 1 minus Q out over Q in. Okay. So which one version do you guys want to use?
The first one.
The first one, this one? All right, so this one, we need to find work net, and then we need to find Q in, all right? So Q in, so COE and work net out. So what's our work net out is either this version, where we can either use this or use this, right? So working it out is either the work of the turbine minus the work of the pump, or it's Q in minus Q out, right? So if we set up our COE open system, one inlet, one outlet. We can do this for heat in, right, that we need. And that's 2 to 3. So do we want to use this or this to get our work net out? Do we want to use the works or the heats? I'm gonna pick then the heat. Okay, someone said heat and the text. Okay, just because it minimizes the number of COEs we got to do, and that's the way I have the values. Okay. Both of them's the same, but you gotta just do one extra COE. All right, so if we do, so that means we have heat in, we have a relationship at least. We don't have enthalpy. We have our enthalpy at 3. We don't have information at 2 yet, so we'll have to do something with the states. If we do heat out, that's 4 to 1. We're going to get H4 actual minus H1. And that one we end up having both of those already, okay? So we get 2090.7 kilojoules per kilogram. All right, so then we need to figure out our enthalpy at state 2. Okay. So we need to figure out information for state 2 actual. Would we do the same we found for this? So using the pump efficiency. Yeah, so we'll have to use that pump. I put P at the top, didn't I, when I said givens? Yeah, this should be, sorry, the givens should be pump. All right, so our thermal efficiency, or not thermals, isentropic efficiency for the pump is going to be the isentropic work on the numerator, because it'll be smaller, the work you have to put in, and then the actual on the denominator, okay? Because you're gonna have to put in more work to overcome the irreversibilities. All right, so we have this. The one thing that changes for a pump is for actual, this is easy. We have H2 actual minus H1. But for the isentropic work, we don't have much information in the tables for compressed liquids, right? There isn't a good compressed liquid table. It only ends up being there until you're at like 5,000 kPa or 5 megapascals. So what we do is use that, as we showed in the slides, the reversible steady flow work equation for pump. Since we can for steady flow, we basically use this equation. Okay, since for the pump, we can take the specific volume out of the integral, we just get V change in pressure. Turbine, we can't use this because the specific volume's changing so much through as you're expanding. But the pump, the specific volume, we can say it's incompressible, and we can utilize this equation for the isentropic work. But again, for the turbine, you can't because that specific volume is changing. And so we use it for the pump. It makes things a little easier. We don't have to worry about trying to get values from for compressed liquid. So we then can utilize just grabbing the specific volume at state 1. We have both of these pressures. Okay. We have the enthalpy at state 1. So I need to just write this value in the table because we already fixed state 1. And then we know the pump efficiency was given. So we can utilize that to get H2 actual. Okay. All right. So let's put that in the table. We get our specific volume for state 1. So now we have that. So we can get H2 actual then. Which is 203.68. Oop, I put in the wrong column. All right. Let's try that again. 203.68 for our enthalpy. Now we have the enthalpies at state 1, 2, 3, and 4. Okay, so then that would be enough to solve our problem. So we have now H2. Okay, so we can get Q in. Which is 3171.4. Then we get. So we can use Q in minus Q out to get a work net out. So we get 1080.7 kilojoules per kilogram. Okay. And we go back up. We have now work net out and Q in. So we can solve for our thermal efficiency.
How do we get our efficiency?
Where, this one? The pump efficiency?
The pump, yeah.
It was given in the problem. I said compressor, I think early, and it should be pump. I put
okay.
subscript C, it should be subscript P, pump.
And then why did we use V at state 1 instead of like opposed to 2? Or does it matter?
Why did we use what? Sorry. I want to say volume so bad, not volume. Specific volume? Which one?
Yes.
This one? We use V delta P instead of enthalpies. Is that what you're asking for? Or why?
Why did we use it at state 1 instead of like state 2? Because because it was constant?
Yeah, so we're using this. This is equal to delta H. So this whole thing on the top is equal to H2S minus H1. Okay. So this change in enthalpy from state 1 to state 2, isentropic, is equal to V delta P. this specific volume change in pressure.
But our volume at state 1 and state 2 are the same.
Oh, because,
That's why-
yes, yeah. So that's why we use 1. We know information at 1, right? And we're assuming it's incompressible, so those would be the same, yeah.
Okay, thank you.
Mm-hmm. All right, so then we can get our thermal efficiency, which is 0.341 or 34.1%. If we look for isentropic, yeah, so that's, you could just rearrange this to get H2S. Okay, but finding H2S in the tables directly is very tough because, again, there's no compressed liquid tables at that low, those low pressures, because so it becomes challenging to get these changes. All right. So then we have thermal efficiency. The last thing that we're being asked about is the mass flow rate of steam. Okay. So any ideas?
We can use the power output.
What was that?
We can use the power output.
Yeah, the power output. Okay, so our power, the net power output that we're given has the energy per unit time, right? So it has that time part. So that's where we bring in. If we think about this, the net power out is the mass flow rate of steam times the work net out, because this is work per unit of mass, right? So if we just multiply mass flow rate times this, we're going to get our power, okay? So we can use this. We had work net out. Okay, we're solving for mass flow rate of steam, and they told us the power net out, right? So we have that. Okay, so we can just utilize this to solve for our mass flow rate of steam, or basically our scalar. They told us, all right, you have the cycle that's at these different states, but now we're going to utilize this cycle at those states for 210 megawatts, right? Okay, so that means, okay, to utilize those states, that means we need to have a mass flow rate of steam that's going to be 194.3 kilograms per second. Right, if we only wanted a 1 megawatt Rankine power plant, then we would have, one, you would basically divide out 210 by this, what we had, or you'd have 1 megawatt on the left and then solve for your mass flow rate of steam required to do 1 megawatt of power output, okay? The other common mistake I see with this is it's the net, right? So you couldn't just grab the turbine's values and utilize it, because the work net out is the work of the turbine minus the work of the pump, okay? Any questions?
Yeah, if we were not given the power output of the power plant, is there any way to find the mass flow rate?
No, you need some. You would need the heat out at the rate at the condenser or something. So you need something else. You can get the thermal efficiency without knowing the scale of the plant. Okay, but with you need something that has a rate in it, right? So that's where the net power output is a rate. We would need a boiler, the heat amount of we would be putting in all in the rate terms, not just in the per unit mass terms.
Got it. Thank you.
You know, what you said earlier, the work powering the turbine and the work leaving are two different.
Right. Because some of that work is from the turbine is going back to drive the pump, right? So what's actually going to leave to be, right? What's actually going to be the net that leaves to go, say, to a generator is going to be, you know, the turbine's driving that pump work. So it'll be turbine minus the pump. Okay, so I just saying that because I know people will just focus in on the turbine and then just forget about the pump. Okay, but net tells us we're looking at everything from work, right?
Okay.
Anything else? All right, so then let's do, we'll do it's a more challenging one. We'll do 10.5.3. All right, I had a nice long paragraph to read. All right, so consider an ideal steam regenerative Rankine cycle with 2 feed water heaters, one closed and one open. Steam enters the turbine at 10 megapascals, 600 degrees Celsius, and exhausts to the condenser at 10 kPa. Steam is extracted from the turbine at 1.2 megapascals for the closed feed water heater and at 0.6 megapascals for the open one. The feed water is heated to the condensation temperature of the extracted steam in the closed feed water heater. The extracted steam leaves the closed feed water heater as a saturated liquid, which is subsequently throttled to the open feed water heater. Show the cycle on a TS diagram with respect to saturation lines and determine A, the mass rate of steam through the boiler for a net power output of 400 megawatts, and B, the thermal efficiency of the cycle. Okay. All right, so we got a lot to have, and they also give you a schematic on this one. Okay, so it's not just the paragraph and trying to figure out what that all means. We have a schematic to go along with it. Okay. All right. So let's get started here. We have ideal regenerative Rankine. The turbine pressure in is 10 megapascals. The turbine's temperature in. So this one I'm just doing the subscript general because we don't know the numbers yet. I mean, I do, but there's a lot of things going, a lot of states, so we could, they also give us the schematic, so we could put it down, but I'll just leave it like this for now. All right, so we have 600 degrees Celsius. We have the condensation, the condenser pressure is 10 kPa. A little bit of tricky, no, not yet. The turbine, we have an extraction, so that means we're pulling some steam off at 2 different locations. There's one. So turbine, extract, 1 is at 1.2 megapascals. There's a second one being pulled off at 0.6 megapascals. And there's a couple things that are a little bit more tricky, but they tell us the temperature out of the closed feed water heater is equal to the saturation temperature, so Tsat, of the extracted steam, okay? And then the quality out of the extracted steam on the feed water heater. This is the closed feed water heater. Is 0, so it's a saturated liquid, it told us. Okay, so they want us to find part A, the mass flow rate of steam through the boiler. For a work net out of 400 megawatts. And then part B is the thermal efficiency. Number of states, yeah, this one has 11. I mean, I think I've done we have the combined cycle, which maybe it doesn't have 11. But I've done, not for class, but for work, I worked for GE Power Systems for a little bit, doing when actually it was an internship way back when, and I actually did analysis like this for them on big scale power plants, looking at changing the seals through turbines. So through the stages of the turbines, changing this type of seals they were using, and they wanted to sell this to these power plants. GE did this change of the seals, so we had to analyze and look at how the work would change. Basically, they would lose less water through the stages, and then analyze what that work net and power net that they'd end up getting when they changed out the seals. So that had way more than this. Okay, this was basically, I was looking at schematics of power plants that were, desk size, so they were huge. Okay, you open them up and it's just like all kinds of information across the whole thing. Okay. All right, so schematic. We have our boiler. Oh, let's see if I can do this better. All right, we have our boiler. We're going to have our turbine. That's going to go into our condenser down here. All right. Let's see if I can fit all the components easily here. We got a closed feed water heater. Got a pump. Open feed water heater. and another. So stop touching. All right, and then another pump. Okay, so let's just move this over for cleanliness. All right, so we have the condenser over here. We're going into our first pump. Okay, so this will be our state 1 right here. All right, so we have our pump 1, our first pump. Okay, we go out of that pump and we're going into the open feed water heater. Okay, so that's state 2 right there. Okay, so then we have our open feed water heater. So this is open feed water heater. Okay. The open feed water heater is basically a mixer, right? So 2 comes in, and then we have a bunch of other things that are coming in for it. But for now, we have what goes into and leaves the open feed water heater goes into the next pump. Okay. And that'll be state 3. Okay, so this is pump 2. All right, so what leaves that pump goes into the closed feed water heater and flows basically right through it, right? Because the closed feed water heater, the pipes are connected. Okay, so that's then state 5 that it leaves. So this is our closed feed water heater. Closed, okay. All right, then we have our boiler.
Professor?
Yeah.
How come you don't have a state between like pump 2 and the closed feed water heater?
What are you talking about? There it is.
Oh, yeah, okay. Okay, thank you.
No, thank you. Yeah, I forgot to write that. So that's 4. We got our boiler, and then we leave the boiler, and we go to our turbine. Okay, and this is state 8. Okay. All right, so this is where we start extracting steam, and they go different places. So the last end up at the exit of the turbine will go to our condenser, and that's called state 11. Okay, but we have 2 places where we're extracting. First, we extract and we go to our closed feed water heater. That's a very crooked line. And that'll end up, so go right through because it's just a heat exchanger. Okay, and we're at this lower pressure. And usually when you have a closed feed water heater, so this pressure, if you want to take the exit of the closed feed water heater, you either have to go to the right or to the left. To go to the left and go to the boiler's pressure, we would have to have a pump and then a mixing chamber to take it to the boiler. And that's what they saw in the lecture slides, okay? Or because we're at a different pressure than 5 and 8, we're at a lower pressure. So we would have to pump it up to the boiler pressure, or we can drop its pressure. And that's what we see in this problem, is we drop its pressure and we take it to a lower pressure, and we're taking it to the open feed water heater and just using that excess thermal energy to help preheat 2 to 3. Okay, so we got to label these states though. So we have, out of this, we have 9. It exits the closed feed water heater as 6. And then we have it exiting basically a throttling valve or trap. You know, it's just dropping the pressure, and it exits that at 7. So then we can get to the pressure to put it into the open feed water heater. Okay. All right, so that's 7. Okay, so that closes that loop. Now we extract some more steam at a little bit lower pressure. Okay. And we're going to take it and put it into the open feed water heater. Okay, and this will be state 10 right there. Okay. And that concludes our states, right? So we have our turbine. So we have heat coming in to the boiler. Let's do it this way. Heat leaving at the condenser, right? We have work of the turbine, but we're putting in work at pump 1, and we're putting in work at pump 2, okay?
Professor, for the pumps, is the work coming from the turbine?
Yeah, so the turbine is our work out. So to drive some of the cycle, we have to pull off some of that work, right? Or it may, I mean, in an actual system, it may be driven directly. It may go to the generator and then pull some of that energy off. But what's going to end up leaving the power plant is still turbine minus pump work, right?
Okay, thanks.
All right. Now we have a serious table to do, right? We're not messing around anymore with 4 states. We went all the way from 4 to 11. Yeah.
Yeah, the area between state 6 and 7, is that just like a sink, or because you said that's where the pressure dropped, right?
Basically, I have it drawn as like a valve. So what I normally have for like a throttling valve.
But it's not like an actual, like, I guess, piece that needs to be
It is a piece. It will be a piece. So, I mean but that's like what the drawing looks like. So yes, this will be like a throttling valve or a valve or a trap, they might call it. It's a device that drops its pressure.
Okay, but it's not like where heater work is happening. That's
Correct.
just.
It's just
Okay.
a device that is dropping pressure, right? All right, so then our table. Oh, actually, let's do our TS diagram. And then we can do our table here. All right, so TS diagram, we got a vapor dome. And how many pressures we have, we can look at the turbine. So we have one high inlet, then we extract 2, so those are at different lower pressures, and then we exit at the lowest. So we have 4 pressures with the turbine, right? So that'll be 4 lines here. one's always a challenge to draw. You'll see. All right, so if we start at our inlet to the lowest pump, okay, so after the condenser, so state 1, right to the lowest pump, we're going to start right there, okay. Then we isentropically compress to state 2, okay. State 2 is in an open feed water heater, so that's mixing with everything else to get the outlet of 3, okay. But 3 is the inlet to the next pump, right, pump 2, okay. So that means we have to start for 3, quality of 0, okay. Okay, so if we go back up and look 2, so everything 2, 10, and 7 are mixing to give us 3, and that's an outlet, and it's going to the pump. The pump has an inlet, quality of 0, okay. Now we have second pump that raises its pressure all the way to 4, which is equal to 5 and 8, because it's a closed feed water heater. So these aren't, it's not mixing the fluids, so there's no mixing, so that doesn't have to be the same pressure as 9 and 6. So 4, we raise the pressure in the pump 2 to, that's the 5 and 8, okay. So that's the highest pressure. So that means we're going all the way up here.
Professor, you forgot to draw one of your lines on your pressure lines on your graph.
Yeah, I left it off on purpose.
Okay.
I mean, we can draw it. It just because it gets muddled over here with all the things going on. You'll see. I just didn't want to draw that also. We can. I'll draw it maybe after, just so because there's a lot of states over here. So this is 4.
Okay. Thank you.
Mm-hmm. Right there. And then 4 in the closed feed water heater. Okay, so 4 ends up going through the closed feed water heater, and it gets warmed up, and it's the outlet of the closed feed water heater that gets to be the same temperature as the extracted steam in the other one. So we'll see it's right. It ends up being right here at 5. Okay, and now we're out of the closed feed water heater, and we go through our boiler, and that takes us all the way. We're adding entropy because we're adding in heat, and that takes us all the way to our superheated region right here. So that's 8. Now we can expand through the turbine, right? And if we expand through the turbine, right, we expand isentropically, we would go all the way down through all this to our lowest, which is 11. So we didn't have an isentropic efficiency, so we just have an isentropic process from 8 to 11. And the extracted values then would just be 9 right there and 10 right there, okay? And then 11 is our condenser. Takes us back, okay? All right, so now we can do the extracted portions. Let's start with, let's do the lowest, 10. Okay, so 10 goes into the open feed water heater and goes to 3, right? So that's exits, it's state 3 in the open feed water heater. And 9 is a little more challenging. 9 goes through the closed feed water heater, okay, and exits at 6, okay, and that told us it's actually something in the givens. It told us that it leaves as a saturated liquid right there, okay, at 6. And then we go through our trap or our valve from 6 to 7, and that drops pressure. And just like we saw in the earlier chapters, the valve is isenthalpic, constant enthalpy. What that looks like is this, because we're dropping it down to that lower pressure so it can go into the open feed water heater and mix those. Otherwise, we would take the outlet of 6 and raise its pressure up to the pressure at 4, 5, 8, right? Right, so I think that's it for the diagram, okay?
Will this problem be in the test or similar?
Potentially. I mean, on the test, just for any of these, the cycle problems take a long time. So what I would do for any of these problems is I give you most of the problem and I just leave out a strategic bit of it that should only take 5 minutes, 10 minutes, something small. But so this problem that right here that would take, you know, a very long time to do from start to finish, I could give you 95% of the problem and just leave out, like, or give you a table of states, right? But just leave out a few of the states, okay, so that you would have to understand a couple things and then just solve from there. Like, it would strategically leave out just a little bit of information. So it wouldn't require however long it takes to do this problem. It would only require a little bit of time, okay? So any of these problems really take longer than could be done on the test, so I usually leave out things and give you more information than your homework gives you, right? When you're doing it in homework, it gives you the very minimal. So I usually, on a test, give you more than that, but leave out certain things, okay? Just because of time constraints.
All right, thank you.
Mm-hmm. All right. So we would have our table. So we have, in this case, 11 states. So we got to do our table with state, temperature, pressure, enthalpy, entropy, specific volume, all right, so we have 11, but no isentropic and actual, so it's all just actual. And it looks like we'll be finishing this the next class. The good thing is, with this being online, I don't have to rewrite all this on the board and come in early. So that's what usually happens when I do these problems that are cycle problems, because we really need the table and the schematic and the TS diagram. So if it's a problem like this and we didn't finish it, I rewrite that whole thing on the board again. So I'm just going to finish the table and then call it a day. We'll finish the rest of it next class. If I can draw straight lines, which I inevitably can't as soon as I say that. Make a little squiggle. Oh man. Okay, so we have our 11 states, and we'll start walking through it next class. There's just a little bit of understanding at the beginning, and then it starts coming together once that happens. All right, so I'll leave it there for today. Any questions? Oh, wait, can you?
Oh, for the TS diagram from going from like 8 to 9 to 10 to 11, why did we assume that was isentropic?
8 to 9 to 10 to 11. There was no isentropic efficiency on the turbine. So we, as a turbine, then as a Rankine cycle, it spans isentropic all the way through, right?
Oh, and that's
Otherwise,
always for Rankine.
Yep.
Okay.
It's always, yep. And then, yeah, you can insert a table, but then I insert it and I start moving on to the next part of the problem, and you guys are still drawing your table. Okay,
Yeah,
so
I appreciate you doing that.
so I know there are features where I can do it, but then I'd be losing you guys 10 steps ahead. So that's the challenge there. Can I explain again? State 6 to 7 to 3, the trap part. Okay, so this is a valve. So just like a throttling valve, they might call it a trap, and that's more just to capture a bunch of it and then expand it through, put it through an exam. I think we even had a valve. So any of those valve problems where you're basically going from 6 to 7, you do your COE, it's just work, there's no heat, you're neglecting kinetic and potential. So the only thing you have is the enthalpy being the same from 6 to 7. So the enthalpy is isenthalpic, so it's a constant enthalpy. So this is a constant enthalpy process, 6 to 7. Okay. Now, in this open feed water heater, 10, 2, and 7 are all coming together, and the outlet is 3. So it's all just mixes and exits at 3. Okay. When you exit the closed feed water heater, right, I said it went through a valve because you either have to drop its pressure to join someplace at a lower pressure in the system because you're stuck here at 6, right? So and that's what is happening with the valve, or just not putting in extra work, just using a valve, drop its pressure and put it in the open feed water heater. Otherwise, if we wanted to raise its pressure, we'd have to put it in a pump to get it into a section over here and put in like a pump and a mixing chamber to raise and put it into the higher pressure section. Okay. All right, so that's it. I went way over on class. We'll finish this next class. All right. You guys have a good rest of your week, and I'll see you guys on Monday.
All right. Thank you.